Today we are going to learn on Lagrangian and Hamiltonian dynamics. So Lagrangian equations we know, and what we know in our previous classes, that the idea of functionals to the Euler-Lagrangian equation, what is called the degree of freedom and generalized coordinates, Hamilton principle and Lagrange's equation, and we are also we have done some problems on Hamiltonian's equations and Lagrangian's equations and solve for the practical problems, and idea of cyclic coordinates, conservation principles, and so many things, what is called Poisson bracket, and time variation of the dynamical variable in terms of Poisson bracket, that is the equation of motion. We all know this. Keeping this in mind, we are going to now learn on Lagrange's equation for the cases of semi-holonomic constraints and the evaluation of constraint forces in general, and do some simple problems with both time dependent and time independent constraints. Then the second part of my lecture will be consisted of canonical transformations, generating functions, and their problems related to this. So let us start from the very basic degree of freedom knowledge. That the degree of freedom, we all know that the number of degree of freedom of a dynamical system consisting of n particles is 3n minus m, 3n minus k. It is written over here 3n. Why 3n? Because the dynamical system consisted of n particles can move in 3 dimensions. That is why 3 is here, and n is the total number of the particles. So 3n will be the degree of freedom, but if there is some constraints and the number of constraints is k, then the degree of freedom will be reduced by k, and the net degree of freedom will be 3n minus k. So 3n minus k is the measure of the degree of freedom for a system of particles in 3D, for the 3D motion. And here it is written that the degree of freedom is the smallest number of coordinates required to specify the complete configuration or the state of the system. That is, if you have n particles in a system which is moving, so you have to deal with 3n number of coordinates. So and if there are k constants, so we have to deal with 3n minus k coordinates. So this is the minimum number of coordinates you can use to solve a problem. You can use a large number of greater number of coordinates than 3n minus k, but the smallest number of coordinates you should deal is 3n minus k in the case of constraint motion. And the generalized coordinates are those which are independent to each other, and the number of the generalized coordinate for a system of particle is just equal to the degree of freedom of the system. So idea of generalized coordinates are summarized here, the 1 to 3 points, and I have discussed it. Now a position vector of a particle within a system is most important thing, because if you know the position vector, then you can find the velocity, acceleration, then force, and then everything related to the dynamical state of that body. So let us take r1, r2 dot 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 rn are the position vectors of that system which has n number of degree of freedom, small n degree of freedom, that is small n generalized coordinates, and the coordinates are written here q1, q2, qn, and the name generalized coordinates. Why they are generalized? Because these coordinates they see the first point, the coordinates need not to be lengths all the time. It may be angles, it may be another thing. So they are generalized, no fixed dimension is here, and these generalized coordinates are written in terms of q. So q1 to qn, there are n generalized coordinates. So small n is the number of generalized coordinates, distinct generalized coordinates, as well as the total number of degree of freedom. So the position vectors of each particle r1 to r capital N is the number of particles, are function of those small n number of generalized coordinates. So it is written here, the equal to sign will not be there, it is a function of q1 qn and also time explicitly. So the next thing is configuration space. Configuration space is the space related to the n generalized coordinates, that is n dimensional space. So this is not the exact space where the system moves. The system moves we can see in only the 3D cases, but it is an n-dimensional space. So the point, each point in this space will state the dynamical state of the system, the dynamical picture of the system at a particular time. But the curve which we get in n-dimensional space by plotting q1 to qn in n axis, the curve we obtain is not the actual path of the system. So it will be kept in mind when dealing with configuration space. It is a mathematical picture which will enable us to identify the system where in what state the system is. Next thing is the most important thing for this class is the constraints. What is the constraints? When the motion of the dynamical system is not permitted to extend freely, we have discussed it, the limitations of the motions are called constraints. So constraints are classified in actually 4 types. The first 2 types are the holonomic and non-holonomic constraints. Holonomic constraints means if the generalized coordinates are related by an equation, by so many equations, then the constraints will be called the holonomic constraint. See here, it is a function f of q1 to qn, and explicitly time is there, but we can we are not studying here the relativistic phenomena. So time is another independent thing, and this equation, there are k number of equations. K is the number of constraints, and j runs from 1 to k, means there are k number of such equations. Here one equation is written for jth state, for jth constraint, but the number of constant is total k. So equation 2 just denotes k number of different independent equations, where the equation is consisted of those n generalized coordinates. So these are the constraints. These constraints are called holonomic constraints, and for this the generalized coordinates are reduced in number. And now let us take an example of holonomic constraints, where the constraints or the generalized coordinates are related to equation with the equation. So let us take a particle rotating along a circular path, which is constrained to move along the circular path. It can't depart from the circular path, that is, it can deviate from that path. So always x square plus y square, that is the position coordinates of the particle, will be equal to a square, where a is the radius of the circle. So you can see here that if you take x as an independent coordinate, then y will be dependent on x. So the general problem is to solve a one-dimensional problem. The motion is no longer two-dimensional. So these are the holonomic constraints, and if we get this equation of constraint, then you can see that the problem is much more simpler. The Lagrangian equation you can solve. It will help the for the solution of the Lagrangian equation. That is, one dimension is cut off from this equation. And another most important thing, that holonomic constraints are also known as integrable constraints. Why integrable constraints? Because let us take an example of, these are differential form of constraints. Not always we have the actual relation between the coordinates. We may get some in some cases the differential equation of the coordinates among the coordinates. Let us take an example, x dx plus y dy is equal to 0. This is also the equation of constraint, but in differential form, and one can easily integrate it out. So the results of integration will be this: x square plus y square is equal to a constant square, which may be a square. So these are the differential form of the constraint equation, which can be integrated. And the holonomic constraints are those which have the differential constraint equation which can be integrated out. So it is written here, that is integrable constraints. But in some cases, let us suppose x is there, x into dx, it is very easy to integrate. Or you if you put y in place of x, then it is also easy. If y is there instead of x, then it also can be integrated out, and x in place of y, it is also easy. But in place of x and y, if there is a very integrate function, like say y to the power 5 minus x cube, and in place of y there is a xy to the power 10 minus y to the power 155, then it can be integrated. So we can't get this kind of relation where the coordinates are related to each other, and we can take out a dependent coordinate from this equation. This type of difficulty, or this type of constraints, are called non-holonomic constraints, and these non-holonomic constraints have a differential form, may have a differential form like this. See, the form is like this. If we compare with the holonomic constraints differential form, the form is much more similar, but not integrable. Not like this simple your circular equations, circular paths equation. Let us understand how this equation has been written. This is the differential form of the non-holonomic constraints, where ajk is a coefficient and dk is the differential of the generalized coordinate, and dt is a differential form of the time. And j, remember, j is equal to 1 to m is the number of constants, which I have written there. The k is the number of constants, but here it has been changed. It has been changed to m, and k is equal to 1 to n is the number of degree of freedom, or the number of generalized coordinates. So ajk is a function of function consisted of partial differentiation of a function fj, So we can't guarantee it that it can be integrated. If integrated, then the constraint equation will be called the holonomic. If this equation is not integrable, then the constraints will be called non-holonomic. These are the things. Let us take an example on that. Let us see this picture. The C path is a circular path which is lying on xy plane, and Z is the is a perpendicular to the xy plane, and a disc having radius small a is rolling along this path. That is, a coin, 10 rupees coin or 5 rupees coin is rolling in a circular path. So let us take for the time t is equal to t, where the bottom end of the disc is at point P. If you draw a tangent to the path, then it will make an angle theta with the x-axis, and after a time dt, the point P will shift towards your left side by an amount ds. For this motion, the angle phi will change by an amount of d phi. So here first you have to think what are the coordinates you need to describe the motion. The coordinates are x, y, theta and phi, because xy the position of the point which is changing. Okay, theta, as the xy changes, theta also changes, and the disc is rolling. Because of that, phi is also changing. So there are 4 coordinates, and which changes in the time dt by an amount x to x plus dx, y to y plus dy, theta to theta plus d theta, phi to phi plus d phi. Now we have some constraint equations. How? Let S is equal to a phi. S is the arc length of the circular path. So you can take S is equal to a phi, or ds is equal to a d phi. So ds is the actually linear displacement of the rolling disc within the time dt, and d phi is the angle traversed by the radius vector of the disc. So ds is equal to a d phi is very simple, and you can break it into 2 components. ds is a straight line along this direction, this tangential direction, so it has 2 components, dx and dy. So, dx is along this direction and dy is along this direction. So dx is the ds cos theta, that is a d phi cos theta, and dy is similarly a d phi sin theta. Now these 2 equations cannot be integrated out because we don't know any functional relationship theta and phi. So we can't simply integrate it in terms of and get the value of x in terms of theta or phi. Similarly, there is a difficulty to solve the y from this equation 4a. So these are the examples of non-holonomic constants. You can see here the general form of the equation is written here, a into dqk. So dqk, the generalized coordinates, you can think the generalized coordinates in my case are 4, dx, dy, d theta and d phi. So let us see, dx, the coefficient of dx is simply 1, and the coefficient of d phi is simply a cos theta. So a1j is 1 and a2j is a cos theta. So in this manner we can find these ajk coefficients from which are the coefficients of the differential of the generalized coordinates. And see, these equations, there are n number of equations like equation 4, because J runs from 1 to m is the number of constraints. So here you can see also we get two such equations. So number of constraints are 2. So the difficulty of non-holonomic constraints is that it cannot be expressed into a functional form. So there is another example where the inequality comes into play. That is, here at least we get some equation with equal signs, but here see, in case of a particle moving on the surface of a sphere, the position coordinate is x square plus y square plus z square is the distance square from the center of the sphere, that is the position of the particle. So it can be greater equal to the radius of the sphere, because the particle cannot penetrate into the hard sphere, but it can fly up the sphere. So greater than a square can be possible, but not less than, and equal is also possible. So inequality is there. So inequality means you can't take a coordinate as independent or dependent, so it is hard to handle here. These are the examples of non-holonomic, and between these two examples of non-holonomic constraint, we can say this type of non-holonomic constraint cases are often called the semi-holonomic constraints, because although these are non-holonomic constraint, but it can be figured out by a mathematical trick called Lagrange's undetermined multiplier, and so for this reason this kind of constraints are often called semi-holonomic. So, and there are another two type of constraints, scleronomic and rheonomic. When the constraints are function of time, those are called rheonomic, and when it is independent of time, it's called scleronomic. For example, there is a pendulum. If the length of the pendulum is a function of time, that is, it is written here, see, it is contracting with respect to the time. When time rises, the length of the pendulum gets contracted. So the constraint here is a function of time and is just called rheonomic. And if the length of the pendulum remains constant with time, then it is called the scleronomic constraints. And here the constraint is simply holonomic also, because the position of the bob is xy, so x square plus y square is always b square. So it is written in terms of equation. See, there is equation. So it is holonomic constraint. And the constraint means another thing. We are dealing with all time that we are saying that this kind of equation is called equation of constraint, or the differential form of the equation of constraint we have seen here. So equation of constraints or the differential equation of constraints, these two kind of things we are studying here. But remember one thing, the constant is not by a God gifted thing. It has to be come from a physical force, which is called the force of constraint. Here in this case, for the pendulum case, the constraint is the tension in the string. In the case of the sphere, the particle moving at the surface of the sphere, the constant force is the normal reaction of the spherical surface. In this case also the normal reaction. So these are the causes of constraints, the constraint force. We have to find out. We have to find it out. That is our next topic. Here there is a backstage idea which is written here, that you should know some things. That is Lagrangian methods. How we solve the Lagrange's equation of motion. We just identify the generalized coordinates and solve the Lagrangian equation of motion. And if the constraints are holonomic in nature, then we can separate some generalized coordinates as well. So the first step should be minimize your generalized coordinate depending upon the equation of constraint, then move on to the Lagrangian equation of motion and solve it out to get the position velocity what you want. But if the constraints are non-holonomic, what we should do? We should use the method of Lagrange's undetermined multiplier method. It should be used to solve the Lagrange's equation of motion. So let us take a semi-holonomic, that is a class of non-holonomic constraints, which can be written in this form of a differential equation. Again I am describing this thing, that Q is the generalized coordinate. The number of generalized coordinates are 1 to n. It is not written here, it is written previously. So K runs from 1 to n, and the n number of degree of generalized coordinates are there, and J is equal to 1 to m, where small m is a number of constraints. So we get m number of such equations. So equation 5 denotes a group of m number of equations, that is the equation of differential equation of constraints. So we have to find out first AJK, AJT, those are the things. So let us make our life simple by taking the virtual displacement. Virtual displacement means, you know this thing, that is the displacement of the system for which no time is required. So this is called virtual. It cannot be realized in practice, but this is a mathematical trick. If you add up this trick, you can solve some equation of motion very easily. The previous cases, you can consult any standard classical mechanics book to witness some examples of virtual displacement and its use. So if we consider the virtual displacements of the system, so the generalized coordinates will be virtually displaced by amount of delta q, and for this the time delta t will be 0, as there is no time passage due to the virtual displacement of the system. So the equation boils down to this. And so remember the equation number 6, it is important. If we multiply a constant lambda, then there is no harm, because right hand side is 0. So lambda j is a undetermined constant called Lagrange's multiplier, we will see later. Now the equation 7 is of our importance. Now if we integrate from time t1 to time t2, this equation, right hand side will be 0 and left hand side will be integration upon this thing, and dt is there because we are integrating over the time. Here the time is not the virtual, it is real time, t1 to t2. We want to see the system, how system evolved from time t1 to time t2. So the integration has been done, the number of equation number 8. Now we have, from our previous knowledge, the Hamilton's principle. Delta of LDT is equal to 0, integration LDT is equal to 0. So from here we can find this del L del QK minus ddt over del L del QK dot into delta QK dot is equal to 0. It is proved in our previous classes, so you can consult any standard textbook, the Hamilton's principle. You can see the article called the Lagrange's equation of motion from Hamilton's principle. You can see this step. There are so many steps in between, so I am not doing here. So let us see these equations, equation number 8 and this equation. So basically we can add it up. If we add, then the sum will come out of no, not out of the integration dt over the summation of del L del qk minus d dt, this thing, plus sum over lambda j ajk, and delta qk is taken common. So here you can see that the summation over k is 1 to n. N is the generalized number of generalized coordinates. So here now delta q's are not necessarily independent here, because we can break it into two equations. The first one, k runs from 1 to n minus m, and the second one, k is equal to n minus m plus 1 to n. We can divide it. Now see, in the second integration by parts, the second part of the equation contains how many terms in the sum k. You can see there are just m terms, m, that is the number of constraints. If the number of constraints is 3, then this sum will contain 3 terms. Number of terms within the sum of k is m. So we can take it out, and we can as lambda j, see lambda j comes from there, equation 7. Lambda j is arbitrary because we just multiplied by a constant lambda j from the left hand side, and both side, right hand side is 0. So lambda j is arbitrary. So we can say that lambda j will be those constants for which the integrand of this equation should be 0. Okay, so integrand of this equation is this whole term will be 0. See, it is written over here, equation number 10, del L del qk dot, all these things are written here. It is written for kth term, where k runs from n minus m plus 1 to n, that is m different terms are there. So this equation is not a single equation, there are small m number of equations, and from this, and the number of lambda we have is also small m, because lambda j, and j runs from 1 to m. So m number of equations we have, and m number of lambda we need, so we can solve it out. So we can solve for lambda, that is we can know all lambda 1, lambda 2, lambda 3 dot lambda m from the equation number 10, and put it back into the first part of the equation. When the lambda is known, you can use this lambda. So if this equation is 0, from the condition of lambdas are those constants for which this equation is 0, so the first equation should be 0, and from the condition of second equation is 0, we get the lambda and put the lambda back into the first part. So the first part is here, see, k is equal to 1 to n minus m. So equation number 11 can be solved for the generalized coordinates q, q1 to n minus m terms. Okay, so the generalized coordinates are reduced by an amount of m. Together we can sum up these two equations to form a single equation where k runs from 1 to n. So it is written over here, del L del qk minus d dt over this, and k is equal to 1 to n. We can write it from first line. See here, it can be written from here also, but if we write this from from at the very beginning of the equation of 9 that the whole integrand is 0, which is written in the equation of 12, then you can be able to understand how the Lagrangian undetermined multipliers can be solved. So Lagrangian undetermined multipliers are solved by m equations, and by getting those m number of Lagrange's undetermined multiplier, we can use the rest of n minus m number of equations to solve the generalized coordinates. But together these two things, we can write it down, the whole equation where k runs from 1 to n, and here the sum always contains m number of terms. And it should be remembered that the equation of constants which we used is there, equation of 13, which is just the time derivative of the equation here 5. If you derivative with respect to time, equation 5 on the both side, then you can find that ajk into qk dot plus ajt is equal to 0. dt will be cancelled. So it is written in the equation number 13 again. So you have to remember these two things to solve any kind of problem where there are some constraints. Whether the constraints may be holonomic, may be non-holonomic, that is maybe semi-holonomic, we can solve those equations by these two Lagrangian equation of equation number 12 with the condition equation number written in the equation number 13. So next, what is you can see a very interesting thing. If you take this sum into the right hand side, and it will be minus, and if we multiply both sides by a minus, then ddt del L del qk dot minus del L del qk will be in the left hand side, and the right hand side will be plus sum over lambda j ajk, which is written here qk, because the sum is over j, so j index will not be there, only k will be there, k is equal to 1 to n. So this is just like Lagrange's equation of motion, where qk we know that the generalized force, but here qk will be called the forces of constants, because here qk comes from this equation where lambda j and ajk are there, and qk is a function of qk is function of lambda j linearly. Lambda j appears linearly into the equation of qk. So qk is the constraint force, because this equation comes from the constraint equation. So qk will be the force of constraints, generalized constraint force. Now let us take a first example where the problem tells us that the particle is placed on a top of a smooth hemisphere of radius a. Find the reaction. So reaction is a kind of constant force. You can't solve it like you did in the previous class. So this method of Lagrange's undetermined multiplier is to be used here to find the normal reaction. And if the particle is disturbed, is disturbed, at what height it will leave the hemisphere? It will be found later on. So first we consider this picture. In the hemispherical bowl, a particle of mass m is slipping, and for the slip, the angle theta, polar angle, is increasing. Theta is our here the generalized coordinate, because the motion is 2D. Motion is 2D, but there is a constant that the radius r is equal to a, the particle cannot have a greater distance than a. If you solve this equation by in polar coordinates, then you can simply write that the kinetic energy is half mv square. V is written like this: r dot square plus r square theta dot square, and the potential energy is mg r cos theta, because your height is r cos theta. Height is actually here, yes, r cos theta. So r cos theta means the height from the bottom of the hemisphere. So mg r cos theta is the potential at this point. So the Lagrangian can be written very easily. Remember one thing, here r dot is 0 because r is equal to a is equal to constant. It is a constant condition here. So r is equal to a is equal to the equation of constraint. So dr is equal to 0. So comparing with the equation of constraint, we can write that ar dr plus a, because we are dealing with two coordinates, r and theta. So r and theta, the equation of constants will be consisted of r and theta. So the differential form of the equation of constraint, see from here, this part is 0 because the time is not explicit here. So qk means q1 is your r, q2 is your theta, and k runs from 1 to 2. So ajk into dr plus ajk into d theta can be written from this generalized equation. So ar dr plus a theta d theta is equal to 0 we get from the differential form of the constraint equation. And if you compare with dr is equal to 0, you can write that ar is equal to 1 and a theta is equal to 0. So the two equations will arise for the coordinate r and for the coordinate theta. For r coordinate, we will write the Lagrangian equation, because here the Lagrangian equation will be 2 because k is equal to 1 and 2. So one equation is consisted of r and the second equation is consisted of theta. q2 is your theta. So just put it down in the Lagrangian equation, you will get the simple form of these two equations. You try it your own and you will get this equation. So the first equation contains the Lagrangian undetermined multiplier. So to find the undetermined multiplier first, we will use this technique. Let us suppose a variable p is equal to theta dot. Then theta double dot is equal to p into dp d theta. You put this in this equation b, where the b will assume this form, and this will be integrated very easily. Very easily it can be integrated out, because this equation is not cannot be integrated so easily in terms of theta. So we take the advantage of p here, and it can be integrated. Both side integration will give you p square. In the left hand side, p dp will give you p square by 2, and the right hand side will give you the minus cos theta. So 2g by a minus cos, do it your own, you will get the result. The integration constant by the boundary condition, this you will get 2g by a, but theta dot is equal to 0 at theta is equal to 0 is the boundary condition. You use and you will get this result. So we get now theta dot square or p square. It is known to us. Now put it in the equation a, theta dot square, and lambda will give you this value. Lambda is equal to mg into 3 cos theta minus 2. And now we know the constant force. What we have seen here, the constant force is sum over lambda j ak. Here j is equal to 1. Only one constant equation is there. So lambda into ajk. A1 1, because a12 is 0 0. So A11 is again we found it out, AR, which is 1. So the equation of constant is simply QR is equal to lambda into AR, and AR is 1, so lambda. So lambda means mg into 3 cos theta minus 2. That means the equation of constraint, the force of constraint for the particle moving at the surface of the hemispherical bowl is mg into 3 cos theta minus 2, which is nothing but the reaction on the surface of the hemisphere. So if the particle gets dislodged from the point, say from here the particle just leave the touch of the sphere, then the normal reaction should be 0. If you put the normal reaction is equal to 0, it will give you 3 cos theta minus 2 is equal to 0, so theta is equal to cos inverse of 2 by 3. So this angle is that angle where the particle will be detached from the spherical surface. There is another problem where a bead of mass m slides freely in a frictional in a frictionless circular wire of radius b, which rotates in a horizontal plane about the point of the circular wire on the circular wire with a constant angular velocity omega. Find the Lagrangian equation of motion, and equation of motion that it is oscillatory one, and the second part is find the reaction on the wire by the wire on the bead. See, there is a bead, it is the xy plane, and this circular path is revolving about the point O. The axis, z axis, is at the O, and which is coming out of the plane of the paper, and the whole circle is rotating about this z axis at the point O. In the meantime, there is a particle on the wire, on the circular wire, which have mass m, and it will also rotate with the wire, and it will slide also. So the motion of the particle is in 2D, x and y coordinates are there. So first of all, you should write the x and y coordinates of the particle. It will be very easily, it can be very easily done, that as the wire C, OA is a diameter of the wire. Wire is rotating with an angular speed omega with respect to the point O in the xy plane. So the angle omega t will be described by the diameter with respect to the x-axis. X-axis is the position of the diameter OA when there is no rotation. The system is in just static. So phi is the angular displacement of the diameter OA of the wire, and theta is the angular displacement of the particle on the wire having mass m. So you can find a very easy relationship between theta and phi. So with respect to x-axis, the rotation of m is theta plus omega t. Is very, it can be seen here, and you can break these components and see the b is the radius of the wire. Okay, so b cos omega t plus b sin, it can be done. You will do this. X and y coordinates can be found out in terms of time explicitly, and here also the equation of constant is r is equal to b. That is, the particle cannot leave the wire. If the particle leaves the wire, there is no question of constraint. We are dealing with the constraint, so the particle is revolving with the wire, that is along this circular path. So the R is equal to simply B. So dr is equal to 0. Similarly, AR is equal to 1 and A theta is equal to 0 from the differential equation of the constraint. So the constant force QR is not equal to 0 because AR is there. AR into lambda will be the QR, but Q theta is 0 simply because lambda into A theta is equal to 0. One Lagrangian undetermined multiplier is needed because we have just one equation of constraint. To first solve for the theta part. Theta part, how we solve? Just write the Lagrangian. As this motion is confined in the xy plane, and we can take xy plane, the potential energy is 0. So the Lagrangian is simply t. No v is there. So t is equal to half m into x dot square into plus y dot square, and it can be written like this. So theta is there. So Lagrange's equation of motion, the right hand side q theta is 0. So this simple equation, but see the final form of the equation is theta double dot plus omega square sine theta is equal to 0. So you can solve this equation by the method we have described in the above case, and you will get theta as a function of time. And this is also the equation of simple harmonic motion, where omega square is for a pendulum, it is replaced by g by L. So simply L is equal to g by omega square. So the motion of the bead of the particle of mass m is just like the simple pendulum having length L is equal to g by omega square. It is proved. The first question has been answered. But the second question is, what is the reactionary force on the bead by the wire? So for this you have to solve the first part, that is the second part, R part. For this, let us now write again the two equations for x and y, but not in terms of B, in terms of R. R is equal to B. Whenever you want, you can put B, you can put R. So keep in your mind that R is equal to B is equal to constant. We are just here using the R in place of B, but there is no meaning in thinking that R is a variable. No, R is equal to constant. So again, writing the Lagrangian in terms of R, see here we can write R in place of this B. There is no harm. We can write R in place of this B. So substituting this equation in the Lagrange's equation of motion, you can derive the reason behind that we are writing R, because we want to solve this. Okay, we want to differentiate these things, and after differentiating with respect to R and R dot, you can put B in place of R. See, in place of R, the B is put here, and from there lambda can be found, because everything is known, m, b, omega, theta. In known term, lambda has come out. But see, theta is a function of time. We have seen it from here. So theta is a function of time, so lambda is also a function of time. That is, the constraint is not independent of time, it is dependent, that is, it is an example of rheonomic constraint. So the constant force is equal to lambda into AR, that is lambda into 1, and which is lambda. So lambda itself the force of constraint. Okay. The third example is ladder, which is kept like this, and it is sliding. So not sliding, it is the reaction is, it is sliding, and the reactionary force on the wall, you have to find it out. proceeding in the same manner you can find, but here you can see the two equation of motions, two constraints are there. See the motion of a point C, the coordinate is xy, so x is this length and y is this length and theta is this, so you can write x minus L by 2 sin theta, that is x is equal to L by 2 sin theta, and y is equal to L by 2 cos theta. So if you differentiate both sides, then dx minus L by 2 cos theta d theta is equal to 0, and dy plus L by 2 sin theta d theta is equal to 0. So there are two equation of constants, so two Lagrangian undetermined multiplier will be required here. So that is why lambda x and lambda y, two Lagrange's undetermined multiplier comes into play, and the constant and the coefficients are ax and ay are simply 1 here. So proceeding in very straightforward manner, you can find lambda x and lambda y, which are again a function of time, and it can be solved out. Not solved, how to solve it is written here. The next problem is very interesting one, the disk rolling without slipping through an inclined plane. Okay, and find the equation of motion, constant force and the angular acceleration. So in this case the kinetic part, see the inclined plane having inclination angle alpha, and a cross-sectional view of the cylinder has been shown here, which has a radius r, and it is rolling at the time t. The radial vector rotates by an angle theta, and y is the displacement from the top of the inclined plane of the center of mass of the cylinder, that is a rectilinear displacement or linear displacement. So the kinetic energy is of two type of the rigid body, which is one type is the energy of the CM, and second part is the rotational energy. So energy of the CM is half m y dot square, and the second part is half I theta dot square, where I is the moment of inertia for the rotation with respect to the axis of the cylinder. Okay, so I, we all know that half m r square, it is put down here, and the energy, potential energy, what is the amount of potential energy? With respect to ground, it is measured, you can easily get it, mg into L minus y into sine alpha. L minus y sine alpha is this height of the center of mass of the body. So it is simple, and L is equal to t minus u, you will get this value. So y and theta are there, two coordinates y and theta, and the equation of constant is 1, y is equal to r theta, or dy is equal to r d theta. So the coefficient of lambda, which is written in terms of del f del y, which is nothing but ajk in your equation, that is in previously we have written there. I am going to the very basic in the theory part. See ajk, yes, here ajk into dqk or qk dot whatever. So ajk is written there del f del qk. Okay, and it is written previously, that is ajk can be written as del f del qk also. So you can find it from equation number, it is previously written here, equation of constant in the, yes, here, see equation number 4, ajk can be written as f del f j del qk, because it is a constant, and by chain rule you can write in any time. So some problems are given in terms of del f del qk, but the meaning is the same. There is no confusion in del f del y, it is just a, j, k things. So there are two equations, one for y, one for theta, but there is one Lagrangian undetermined multiplier. So two type of equation can be solved, and from there, from mathematical trick, you can find the lambda, which is this, is equal to minus mg sin alpha by 3. So this is the reactionary force. Okay, see, qy is equal to lambda into this, and this term is 1, so lambda, so minus mg sin alpha by 3, but q theta is equal to c del f del theta has been deduced that it is r. Why r? See, dy is equal to r into d theta. So coefficient of dy is 1, but coefficient of d theta is r, but if you take this in the left hand side, this then minus r. So minus r is written, minus r into lambda, the force of constraint q theta, and the value is this, and this is the time independent constraint again, because there is no time involved in this because alpha is a constant. From here there is another method to solve it. The equation can be solved. See, if you take the second equation, it is easier. There is without the method of Lagrangian and undetermined multiplier, the equation simply you can solve for Lagrange's equation, but you can't get the reactionary force or the forces of constraints. So the advantage of using the Lagrange's undetermined multiplier is that you can find the equation of the forces of constraints. Okay, there are another problems. There is another problem, you can do it your own, you can test yourself whether you can understand it, you can solve it by your own, then it will be of great success. Here the case of again two reactionary forces but one Lagrangian undetermined multiplier. Question, there is a question, and here I have written this for your self study, why Lagrangian method is has been used, but I suggest you after completing the whole lecture you will come into the point. Don't study at this point of time, you will come later and you can understand the thing why Lagrangian method is useful than anything else. You can understand it. But there is a very interesting thing. What is the benefit or demerits of Lagrangian mechanics than Newtonian mechanics? It is a very good comparative study, and if I tell you in one line, there are some salient features. That first thing, Newtonian mechanics deals with the vectors, but Lagrangian mechanics deal with the scalars, energies, work energy, and Newtonian equation deals with the force momentum, that is a vector form. In some simple cases, Newtonian mechanics does a very good job, but Lagrangian mechanics complicate the thing. But when the system of the motion complicates, then you have some difficulties to find the forces and momentum, and the vector sum will be very difficult. And then the Lagrangian mechanics is very straightforward to deal with. The only challenge is the mathematical tricks, the mathematical integration, differentiation, that will be the challenge, but not the physics. You can understand all these things, all these points. You study very carefully and you can understand these things. In the next class we will move toward the Hamiltonian equations and the canonical transformation. So I should stop here and just do the problems by your own, which I have seen. So study them carefully, and we will continue from here the Hamiltonian dynamical system in the next class. Thank you.